Speaking.
All right. Good morning. My name is Michael Lorenzo. This is Eduardo Garcia, Francisco Agarte with the OT10-MagnetocaloricRefrigeration. We're here to present magnetocaloric refrigeration. All right. So a little background knowledge. What is the magnetocaloric effect? The magnetocaloric effect is a phenomenon which causes certain materials to generate heat as a product of being exposed to a magnetic field. This is caused by the alignment of the magnetic moments within the material. And our goal for this project is to be able to manipulate this behavior in order to produce a refrigeration cycle. Here we see a refrigeration cycle for a magnetic refrigerator and a more common refrigeration cycle you might see in your refrigerator at home, which uses compression and decompression of a gas. Now, our project is, in this phase, we have the material, which is demagnetized. We apply a magnetic field to it, which aligns the moments within the material and generates heat. While maintaining the material in the field, we'll be removing the heat. And we'll be removing the heat in an attempt to get back to this temperature. Then, when we remove it from the field, the disalignment will cause the material to drop to a lower temperature than it was initially. Our goal for this project is to design and manufacture a test bench to measure the highest change in temperature that we can exhibit from these materials. Some of the things that we have to consider are the working temperature of the material, the method of heat exchange, and a method of data acquisition. Eduardo Garcia will be presenting our design. Oh. All right. There are currently 11 room temperature magnetocaloric refrigerators in the world. 2 of them are in the United States. One of these is in the Ames Laboratory based in Iowa State. We are working towards visiting Iowa State to see their magnetic refrigerator so we can have a better understanding of the variables we need to consider to get this thing to work properly. Now, Eduardo Garcia will be presenting this.
As you can see here, we have decided to go with a circular design. The reason we're going with a circular design is because at any given time, the material will be in either of the 2 heat exchangers. This would be the heat rejection heat exchanger. This is the cold side heat exchanger. So pretty much, we're going to be using, there's going to be water flowing through here. Inside is a concentric tube heat exchanger on this side and a plate heat exchanger on this side, water to air cooling. So pretty much, as you can see, here's the material. According to Dr. Borso, we were able to manufacture this material. And also the pump, we decided to go with a centrifugal pump due to that we're pumping water, so it's not a high viscosity fluid, so it will reduce costs in comparison to using a positive displacement pump. Here's electronics. You can see we'll be using an Arduino to acquire all the data for the data acquisition. We also would have a laptop, a netbook, which would be integrated into the system to be able to have all the data, graphs, and be able to export it to Excel and so on. And you can use all this information and benefit to the material. Also, here we have the motor. We'll be using a motor to spin the material around. It would have to be a high torque motor, but at the same time, we need to have nice variation in RPM, so we'd be able to test what would be the optimal speed to spin the material around in the chambers. And here you can see different types of thermocouples. We're still deciding which type of thermocouple we'll be using, either type A, type K, or so on. But pretty much we'll be using them to measure the temperature of the fluid, the changing temperature of the material, etc. Now I'll leave you with Frank.
Right, so one of the motivations behind Emacs magnetocaloric refrigeration is to acquire as much data as possible from these materials so that this data may prove useful for marketable MCR systems. Moreover, replacement of current refrigeration cycles with magnetic refrigeration cycles will eliminate the use of these potentially harmful gases such as chlorofluorocarbons or hydrochlorofluorocarbons, for example. One of the benefits in our project is that this will aid in further development of more efficient, at low operating room temperature magnetocaloric alloys. Also, EMIC is trying to make this apparatus in such a way where it would consume low power, and this would eventually yield to less resources needed for the operation of the system. This is very beneficial for those areas, some parts of the world where these resources are limited. Next slide. So our anticipated project budget is about $3,000. This is what we anticipate to have in our pockets. Project cost of the device and fabrication is $2,400. This is, we have different design iterations, and these design iterations differ in the type of materials we're using, the efficiency of the heat exchangers, and so this is only based on our what we think, our most optimum design. 320 hours of labor between us three, and as you can see here, most of our, through the time frame of our project, most of the time that we'll be spending is on research, since this is a new topic for us. Much research is really needed to make sure our system works properly. We've allotted our project fabrication to be within 3 months and 2 months for testing and optimization of the system. That is the conclusion of our project. Any questions?
Is this funded
Yes.
100%?
Dr. Boyzo is currently working to try and acquire some funds for.
We have some already in a couple of places, so yes.
We've also got some money from NACME.
Oh, yes, also design.
From who?
NACME.
Oh, okay.
What type of RPMs are you going to need in order to be effective?
We're still, that's why I mentioned that the motor it will have to be a small motor, but at the same time we'll have to provide enough torque to be able to spin it, but have a variable range so we can test and increase the RPMs or slow down the RPMs and see what RPM will be the most optimal to run the system.
And the fact that we're testing different materials is why we need another range, because certain materials may need a little more time to heat up or cool down.
So you don't really even know your energy balance today, but this,
Exactly. That's why it's a test bed.
Yeah, it's
We
a
need
test
to
bed.
have, this needs to be as versatile as possible for different materials, because each material is going to have its own RPM, its own time, and its own properties. So each material has a working temperature. So that, due to that working temperature, requires different parameters set up in the test bench.
one concern I have is on the project timeline. It looks like you're finishing the production of your equipment 2 weeks before the completion of your test time. That's really short. If you're going to get some of these answers to the efficiencies of systems, you're going to need more time. So if there's any way that you can push in the fabrication time, testing is important.
Yeah, right.
That you're going to make assumptions, you're going to model it, and then you're going to have to prove that your system does what you said it would. And so I don't think 2 weeks is enough time.
All right, well, we'll definitely take into account and try and move back fabrication, have a longer testing time.
More questions? No? Okay.